Trigonometric functions. Let us define. Okay, there's three definitions we'll cover in this section. On the unit circle, on the plane, and by right triangles. This is sort of like the oldest and most traditional, going back to the Greeks. This one is most versatile for dealing with obtuse, breakback, and Pac-Man angles and beyond. Um, this one is sort of a convenient combination of the two. All right, here we go. Starting with the unit circle, because the front cover of the book says trigonometry, a unit circle approach. So here's a unit circle. Its equation is x squared plus y squared equals 1. We put an angle in standard position. One side, the initial side along the positive x-axis. Here's the terminal side. And in this case, it's an obtuse angle, and it meets the circle at x by y. The 6 trigonometric functions will be in terms of x and y. X is called the cosine, written cos theta. Y, the height, is called the sine, written sin theta. Then there are various ratios. Y over x is a tangent of theta, written tan theta. X over y is a cotangent, written cot theta. Reciprocal of x is called the secant of theta. Reciprocal of y is called the cosecant of theta. Now, because of this, if x and y are the cosine and the sine, and these are these ratios, then tangent is y over x, sine over cosine. Cotangent is x over y, cosine over sine, right here. Secant is 1 over x, therefore it's 1 over cosine theta. The cosecant is 1 over y, therefore it's 1 over sine theta. These are ratio identities. We'll be using them a lot. Basically what it means is you write everything in sines and cosines. You can if you wish. Also, because x by y is on the circle x squared plus y squared equals 1, and x is cosine and the y is sine, then the square of the cosine plus the square of the sine equals 1 for any theta. We write it this way, cos squared theta and sine squared theta. I mean, I guess we could just put parentheses around the parent cos theta and parent square that, parent sine theta and parent square that. But I guess someone somewhere along the line got lazy and didn't want to write all those parentheses, and so we have it in this form. Okay, now this defines trig functions via the unit circle. Now I'm going to imagine trig functions on a plane. We have the angle in standard position. Here's the positive x-axis. Here we turn theta radians. Here is the terminal side. And let's have it go out to x by y, not necessarily on the unit circle. Now, if this is the point x by y, then it's out a distance r from the origin, where r is square root of x squared plus y squared. That's by the Pythagorean theorem. So you can imagine this right triangle here and here. This side is x, this side is y. It's a right triangle. R equals root of x squared plus y squared. And, well, the rule is you kind of shrink this down by a factor of r to put it on the unit circle. Then instead of x by y, you get a point on the unit circle, x over r by y over r. So x over r is cosine theta, y over r is sine theta. And then going by all this other stuff, the ratios between tan, cosine, secant, and cosecant, and sine and cosine. Tangent would be sine over cosine. This over this, the r's cancel, you get y over x. Cotangent is cosine over sine, this over this, the r's cancel, cotangent is x over y. Secant is 1 over cosine, so that's going to be r over x. Cosecant is 1 over sine, therefore y over r over y. Now we roll it back to the oldest definition in terms of right angle triangles. So you have a right angle triangle, 90 degrees here. Here's the angle theta. Opposite theta is this side here, we'll call op for opposite. Adjacent to theta is this side here, ADJ for adjacent. And this diagonal is called the hypotenuse in the Pythagorean theorem. So we'll call it HYP, height. And if ADJ corresponds to X, and op corresponds to Y, and height corresponds to R, then right away, cosine becomes adjacent over hypotenuse. Sine is y over r, opposite over hypotenuse. Then the rest basically follow. Tangent is y over x, therefore opposite over adjacent. Cotangent is the reciprocal, therefore adjacent over opposite. Secant is the reciprocal of cosine, so therefore the reciprocal of this is the hypotenuse over adjacent. Cosecant is the reciprocal of sine, therefore hypotenuse over opposite. Now, okay, here's where the reason why it's 6 trigonometric functions, because there's 3 numbers here, adjacent, opposite, and hypotenuse, and there are 6 ways to take ratios of them. This over this, this over this, this over this, and the other way around. This over this, this over this, and this over this. 6 ways, and therefore these 6 functions. Now, if you have a right angle triangle with one angle theta, this will also be an angle, phi, and these are what are called complementary angles. They add up to 90 degrees. Therefore, phi is 90 degrees minus theta. Now, what's opposite to theta is adjacent to phi, and what's adjacent to theta is opposite to phi. But they have the same hypotenuse. And therefore, cosine of theta is adjacent over hypotenuse, adjacent theta, but compared to phi, it's opposite. So you get cosine theta equals sine phi. And by the same logic, sine theta equals cosine phi. And then if you go on to the rest, things swap around. Secant theta is cosecant phi, because these are reciprocals. Cosecant theta is secant phi, because these are reciprocals. And tangent and cotangent, you swap opposite and adjacent, and therefore you swap tangent and cotangent. So tangent of theta equals cotangent of phi, and cotangent of theta equals tangent of phi. In general, a trig function of theta equals cotrig of its complement, 90 degrees minus theta, and cotrig of theta is trig of the complement, 90 degrees minus theta. Complementarity relation. Now there's going to be some special angles. There's a 45-degree angle, there's a 30-degree angle, and there's a 60-degree angle. To find the trig functions of the 45, we draw this triangle here with a 45-degree angle here, and also here, and a 90-degree angle here. Because these will both be 45, therefore these angles are the same, therefore these 2 sides are the same. We set them equal to 1, then by Pythagoras, you'll get that the diagonal equals √2. And then you can read off the trig functions. Cosine 45 is adjacent over hypotenuse 1 over √2, which can rescale as √2 over 2. Sine of 45 is opposite over hypotenuse 1 over √2, and this 2 we can rationalize to √2 divided by 2. Tangent 45 is opposite over adjacent. So that's 1 over 1, which is 1. And generally, when you get to the tangent, the other 3 you just take reciprocals. Secant is reciprocal of cosine, therefore reciprocal of this, √2. Cosecant of 45 is reciprocal of sine 45, therefore reciprocal of this, again √2. Cotangent of 45 is reciprocal of tangent, reciprocal of 1, which is 1. So here are the values. And I think you don't really need to memorize these values, you just need to remember being able to draw this triangle, and then you can read off the trig functions from it. Now here we'll start off with an equilateral triangle. The side 2 and 2, and this will be side 2 as well. We break it up into 1 and 1. Since the 3 sides are equal, the 3 angles are equal, And that turns out means that they're all 60 degrees. And if you look at half of this triangle, where it goes down to 1, well, we have a triangle, a 30, 60, 90 triangle, with this side 2 and this side 1. And if you do a bit of algebra with a Pythagorean theorem, it turns out this side is square root of 3. Now here you can read off the trig functions of 60 and the trig functions of 30. Cosine 60 is adjacent over hypotenuse, 1/2. Sine of 60 is opposite over hypotenuse, root 3/2. Tangent of 60 is opposite over adjacent, root 3 over 1 is root 3. Then the other three are reciprocals. Secant is reciprocal of cosine, reciprocal of 1/2 is 2. Cosecant is reciprocal of sine, and the reciprocal of this is 2 over root 3, which you can rewrite as 2 root 3 divided by 3. And let's see, cotangent of 60 is 1 over tangent of 60, and that'd be 1 over root 3, which is root 3 divided by 3. Now, if you read out cosine, cosine is adjacent to 30 degrees over 2, root 3 over 2. So cos 30 equals sine 60. Sine 30 is opposite the sine angle, the 30-degree angle, over hypotenuse, 1 over 2. And here you can see that sine 30 equals cosine 60. These two are equal, and these two are equal. Tangent 30 is opposite over adjacent, 30 degrees. 1 over root 3, that's root 3 over 3. That equals cotangent of 60. Tan 30 is cotangent 60. Secant 30, well, it should be secant 30, it's 1 over cosine, therefore 2 over root 3, therefore 2 root 3 over 3, like this. So secant 30 equals cosecant 60. Cosecant 30 is hypotenuse over opposite, 1 makes 2. Or it's also the reciprocal of the sine. So reciprocal of sine of 1/2 is 2. And as you can see, cosecant of 30 equals secant of 60. And then cotangent of 30 is reciprocal to tangent 30. Therefore, you get root 3, which is equal to tan 60. So trig of 60 equals cotrig of 30. Cotrig of 60 equals trig of 30. Now, later on, I'm going to prove that this is a right triangle with angles 15 degrees, 75 degrees, and 90 degrees, with a diagonal of 4. Then this short side is root 6 minus root 2, and this side is root 6 plus root 2. And then from this diagram, we can read off the trig functions of 15 degrees and 75 degrees. Okay, here we do some examples. Excuse me for a moment. I need some tea. Herbal tea. I get wired if I drink too much caffeine tea. All right, sine of 11 pi over 2. Now, pi is a half turn. Pi over 2 is a quarter turn. So 11 halves is 11 quarter turns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It goes around this many times and it lands here at the point 0 by -1. Now, the sine of an angle is on the unit of an angle meeting the unit circle is the y value, so its sine is -1. What's the cosine of 11 pi over 2? Read it off of here. What is it?
0?
Yes, it's 0. It's the x value. That's correct. Here we have the expression 4 sine 90 degrees minus 3 sine 180 degrees. What's that? Okay, for sine 90 degrees, we do a quarter turn here. So what sine of 90 degrees? Read it off of this.
1.
1, that's correct. So 4 times 1. Minus 3 tan 180, we go around 180 degrees to -1 by 0. And tangent is y over x, 0 over -1. So we have 4 times 1 minus 3 times 0 over -1. This cancels. This gives us 4. So it's 4. Here they ask for the 6 trig functions of 2 pi over 3 radians. Well, first let's figure out how many degrees that is. 2 pi over 3 radians has 2 pi over 3 times 180 over pi degrees. Pi's cancel. 2 times 180 over 3 is 120 degrees. It is, in fact, 1/3 of a way of a turn of a circle. 1/3 of 360. Now, all right, so here we put an angle in standard position. We draw this. Now, if this is 120 degrees, and what we have here remaining is 60 degrees. So here we have a triangle like this. Now I'm going to make this length 2. And if it, and okay, fine. So this side is, in a 30, 60, 90 triangle, you know, the hypotenuse, the shortest side is half the hypotenuse. And then there's this √3. So it's back -1 and it's up √3. -1/√3 with a radius of 2. So cosine is x over r minus a half. Therefore, the secant is reciprocal, -2. Sine is y over r, √3 over 2. Therefore, cosecant is reciprocal, 2 over √3. Tangent is opposite over hypotenuse, so y over x. 3 over -1 is minus √3. Oh dear. You know what? I'm going to have to change this. Error. I'll have to change page 8. This is this. 2, page 8. Cotangent equals not -1/2. My apologies. It's -1 over √3. It's the reciprocal of this tangent. So it should be -1 over √3. I shall change that after class. Now here they ask for the trig functions of 210 degrees. So we rotate 210 degrees. That's 30 degrees past 180. So we have a 30-degree triangle here. So imagine this triangle here, 30 degrees. The side's 2, and this is down 1, and this is back -3. Okay. And then we proceed. Cosine is adjacent over hypotenuse, minus √3 over 2. Therefore, its secant is reciprocal, -2 over √3, which you can rewrite as -2 √3 over 3. Sine is opposite over hypotenuse, -1/2. And therefore, cosecant is the reciprocal, -2. Tangent is opposite over adjacent, so -1 over -√3. So the negatives cancel. We can rescale it to √3 over 3. And then cotangent is reciprocal of tangent. This and the negatives cancel. No one disappears, and we're left with √3. Now, all right, it's all well and good to be able to find angles of trig functions at 30, 45, and 60 degrees. And there's also 0 degrees and 90 degrees. Fine. Now there's a gap in the between in there at 15 degrees and 75 degrees, and we will I will go over the trig function of that. In fact, it's an extra credit set. But of course, that's only a few angles, and there's only 24 around in a circle. There's of course infinite continuum of angles. So fortunately, modern technology, you can find trig functions. Here it says sine, cosine, tangent, and it even has a mode button which you push and it'll tell you, and you can adjust if it's in radian mode or degree mode. And I think even this one does gradients. Let's make sure. No, it does radians and degrees. So okay. So I can use that to, if I wanted to find sine of 28 degrees or tangent of pi over 10 radians, you can adjust the calculator to degrees or radians and then find sine of 28 or sine of tangent pi over 10 and push a button and get the sine of 28 degrees is about 0.46947. Tan pi over 10 radians, okay, adjust the radian mode, tan pi over 10, write that on the calculator, push a button, 0.32491. So these are by calculator or computer, I suppose. And you can, and they ask these are questions like these are in the homework, and use your calculator. In the old days, they used to add, before calculators or before all the cybernetic revolution, they actually would publish trigonometry textbooks with a table of trig functions in the back of the book. That has gone the way of the dinosaur. So be it. Okay, that concludes material of this class of this evening. Stop recording.